Welcome. Good afternoon. I'm David Tilbrook from the Department of Fundamental and Theoretical Physics, as you probably know, here at ANU, and this is the third seminar of the AIP Theoretical Physics Seminar Series for this year. Just while we're waiting, take this quick opportunity to remind everybody about the upcoming 47th Annual Condensed Matter and Materials Meeting, which is going to be held in early 2025. This is the so-called Wagga Conference because it's normally routinely held in Wagga Wagga, but next year, 2025, it's going to be held at the University of Queensland from the 4th through to the 7th of February. As I mentioned in the last seminar, this Wagga Conference is very relaxed, it's informal approach, and it's well suited to students who are presenting for the first time, although of course it addresses the full gambit of condensed matter physics and scientists, and it's widely supported by condensed matter physicists right around Australia. I believe the abstract submissions and registrations usually open in August and they close later in the year, so you've got plenty of time. But I just thought I would mention it if you're thinking about going, or if you're a student and you want to ask your supervisor about finances or whatever might be available for you to attend, particularly to present a poster or something. Maybe it's a good time to start thinking about doing that and think about what you might want to present. Okay, having done that, today's speaker is Professor Rafael Nepomechie from the University of Miami. Rafael obtained his PhD in physics from the University of Chicago and has held postdoctoral positions at Brandeis University and the University of Washington before joining the physics department at the University of Miami. His current research interests include quantum integrability and quantum computing, and I think, judging by his abstract, he'll probably be touching to some extent on both of those topics in this talk. Over the past few years, we've had a number of talks on quantum computing, dealing with both the physics of various implementations of quantum computing and the development of quantum algorithms for the solutions of specific problems. As you would have seen from Rafael's really interesting abstract, his talk today is on the spin 1/2 Heisenberg quantum spin chain, which has a large number of applications in theoretical physics. I think it was initially introduced, Rafael will clarify this, I'm sure, for the study of magnetism, but it's entered into many different areas of physics, and it has a lot to say in the study of phase transitions, for example. But, and it's interesting, I think, because there exists, in theory, an exact solution called via the so-called Bethe ansatz, as you would have seen in Rafael's abstract. But despite this, in all but the simplest cases, calculations are a very formidable problem. So to tell us a lot more about this fascinating area of condensed matter theoretical physics, Rafael's talk today is entitled Preparing Exact Eigenstates on a Quantum Computer. Thanks, Rafael.
Well, thank you for that amazing introduction. Oops, let me put my timer. So first I would like to extend a big thank you to Murray Batchelor for hosting me here at ANU and for the invitation to participate in this seminar. And also thank you, David, for that amazing introduction and for hosting the seminar. Right, so the title, Preparing Exact Eigenstates on a Quantum Computer. So the work I'm going to talk about was done with an amazing undergraduate student, David Rave, and he's just finishing in Miami, and he'll be starting graduate school at Rutgers in the fall. So by way of introduction, an interesting problem in quantum computing is the so-called quantum state preparation problem. So the question is, how can you prepare a given quantum state, say an eigenstate of a Hamiltonian, on a quantum computer? And this could be of interest for computing, for example, correlation functions of that state. which, as David already mentioned, is hard to do. And so natural question is, which would be an interesting eigenstate to focus on. In my opinion, an attractive candidate would be a beta state, that is an exact eigenstate of an integrable Hamiltonian, because for one, these states tend to be better understood than eigenstates of non-integrable Hamiltonians. And nevertheless, these are often very non-trivial states. And so the goal of today's talk is to show you an algorithm for preparing beta states of the Heisenberg quantum spin chain. And this is work done with David in this recent preprint. So by the way, please feel free at any time to jump in with questions or comments. Okay, so here's an outline of the talk. I'll begin with a brief review of beta ansatz, and then a brief review of quantum computing, basically all you'll need for this talk. And then as a warm-up for the beta state, I'll describe how one can prepare so-called Dicke states on a quantum computer. And then finally, how to generalize that to prepare beta states on a quantum computer. And if there's time, I'll show you a sort of surprising application of this algorithm to finding beta roots on a quantum computer. And then finally, a brief outlook. All right, so let's begin with a review of beta ansatz. So more specifically, let's focus on the closed isotropic, or so-called XXX spin-a-half Heisenberg quantum spin chain. So as David already mentioned, this is a model of magnetism, a deceptively simple one, put forth by Heisenberg. This is a picture of the young Heisenberg at the dawn of quantum mechanics back in almost 100 years ago. So in this model, we consider a ring of L spin-a-half spins, or qubits. Yeah, and these are arranged in a circle, as shown in this cartoon. And each of these spins interacts isotropically with its nearest neighbor. So for example, this guy would interact with the one on the left and the one on the right. And this is, as I said, a simple model of magnetism. And this is the Hamiltonian. Let me explain the notation. Well, first of all, when this sum over n, when n reaches L, we have here L plus 1, which is to be interpreted as sigma 1. So this enforces periodic boundary conditions. These sigma n's are sigmas at site n and identity matrices at all other sites, numbered 1 to L. Yeah, so these sigmas are the familiar Pauli matrices, sigma x, y, and z. And this blackboard I is just a 2x2 identity matrix. And this dot here means that I should sum over the superscripts j from 1 to 3. In other words, the x, y, and z Pauli matrices. Yeah, and in fact, we have here n plus 1 tells us that we have these nearest neighbor interactions. So because we have here tensor products of L two-dimensional vector spaces, this is a 2 to the L by 2 to the L matrix. And again, as David already mentioned, this model has many, many applications. Well, first, it can actually be realized experimentally, and it has connections with conformal field theories, ADS, CFT, statistical mechanics, you name it. Yeah, I think this is one of the fundamental models of theoretical physics. And one of the questions you could ask are, what are the eigenvalues and eigenvectors of this Hamiltonian? So of course you could try to put it on Mathematica, okay, but you wouldn't be able to go very far. So after, say, 10 sites, you're talking about 1,000 by 1,000 matrix. So the matrices are growing exponentially in size with the length. And quite remarkably, just a few years after Heisenberg wrote down his model, Hans Bethe found a remarkable solution, now known as coordinate beta ansatz. And as I'll explain in a minute, his solution reduces the problem to solving a system of polynomial equations. So instead of diagonalizing huge matrices, you just have to solve a system of polynomial equations. And these are known as beta equations. So let's look at this a little bit closer. The main point of the solution is that the eigenvectors of this Hamiltonian are multi-particle states, and often these are called magnons. So multi-magnon states. So the simplest case is when you have no particles, no magnons, so the zero particle state, and that'll be the ground state, actually, of this Hamiltonian. And it's just a tensor product, L-fold tensor product of the 1, 0 vector. In other words, we have all the spins up. And it's not hard to check that this state is indeed an eigenstate of the Heisenberg Hamiltonian with eigenvalue 0. Okay. So now let's turn to the next most trivial state is the one particle state. So here what we do is we flip one of these L spins, say at position X. You weigh it with a factor e to the ikx, and you sum over all positions this flipped spin. And let's call that state psi of k. K is a number here. It turns out that this state is an eigenstate of the Heisenberg Hamiltonian. And then the eigenvalue, I'll write little e of k, is given by this formula, 4 sine squared k over 2. So we can regard this as the energy of the particle, so the one particle energy. Now, this is not true for all k. It's only true provided that this k here satisfies this equation. E to the ikl is equal to 1. So for those k values, this will be an eigenstate, and this will be the corresponding eigenvalue. Okay, now let's turn to the two-particle state. It's getting a little more complicated. What we do now is we flip two spins, positions x1 and x2. We'll sum over these x1 and x2s. And we're going to weigh it now with the following factor here. So this factor here, S, is a function of two variables, k and k prime, a simple formula here. And we also have, and we have this phase factor e to the ik1 x1 plus k2 x2. And here we have the same factor, but with k1 and k2 interchanged and with a relative minus. If I form the ratio of these S factors with a minus sign, I'll denote this as capital S. Turns out this can be interpreted as the two-particle S matrix. So in a space-time diagram, we have these two particles, these two magnons that scatter with each other and pick up this S matrix factor. And it turns out that this state here is an eigenstate of the Heisenberg Hamiltonian, and the eigenvalue is now the sum of these one particle energies, one with K1, one with K2, that I showed on the previous slide. And that's true provided these K1 and K2 satisfy this pair of equations. again, involving this big S factor. So again, if we can solve for these equations for K1 and K2, we plug in, we get an eigenstate, and this is the eigenvalue. Okay, finally, now we go to the M particle state, arbitrary number of magnons. So here's a formula for the state. What we've done now is that we've flipped M of the spins at positions x1 up to xm, and we sum over their positions. So this factor here, A, is just a product of the factors little s that I showed you on the previous slide. And now we're also summing over all possible permutations of 1 to m of these. So we're going to permute the momenta just like we did in the case of 2 magnons. Okay, and these are the corresponding phase factors, the k and the x. And this epsilon sigma is either plus or minus 1. It's the signature of the permutation. Turns out that this state is an eigenstate of the Heisenberg Hamiltonian. The eigenvalue is just the sum of the one particle energies, provided that these k's, so quasi-momenta, they satisfy this set of M equations. So these equations are now known as Bethe equations, and this corresponding eigenstate is called the Bethe state. So if these equations are satisfied by the k's, then these will be the energies, these will be the eigenstates. And if we make a change of variables, so we change from k's to u, according to this formula, and you call uj u of kj, then these equations here take this form. And if you cross multiply, you'll see that these are indeed polynomial equations. We have M equations and M unknowns, these U's. So remember that these spins interact isotropically, so the model turns out has SU2 symmetry, and one can show it's not too difficult that this gives rise to a degeneracy given by this factor L minus 2m plus 1. And furthermore, M, the number of spins to be flipped, can be restricted to be less than or equal to half the length of the chain. So to show you how all this works, let's consider a simple example. Suppose we have a spin chain of length 4, so L is 4. So according to here, the number of overturned spins, M, or the number of magnons, can be either 0, 1, or 2. Let's put our results in a table. So in the first column, I'll list the value of M, then the beta roots for that value of M, the corresponding energy, and then the degeneracy given by this factor. So the simplest case, when M is 0, there's no beta roots. We said the energy is 0. And according to this formula, the degeneracy is 4 minus 0 plus 1, so 5. So in other words, this energy will appear 5 times. Then we can have M equals 1. It turns out if you write down the Bethe equations for M equals 1, there's 3 solutions, which in terms of the U's are 1/2, -1/2, and 0. And then if you plug into the energy formula, this guy has energy 2. This one also has energy 2, and this level has energy 4. And according to this formula, the degeneracy is going to be 4 minus 2 plus 1, or 3. So each of these levels is threefold degenerate. Finally, at the maximum value, 2, M equal 2, it turns out the Bethe equations have 2 sets of solutions. One is plus or minus I over 2, right? These are 2 beta roots, or plus or minus 1 over 2 root 3. If you compute the corresponding energies, turns out for this level, it's 2, and for these beta roots, it's 6. The degeneracy factor, according to this formula, is 1. Okay, and so now if you sum all these numbers, we get 16. which is 2 to the 4, which is 2 to the L. And indeed, if you just plug in the Hamiltonian into Mathematica and you ask for the eigenvalues, you'll get these eigenvalues with these degeneracies. So the beta ansatz is completely describing all the eigenvalues of the Hamiltonian. In fact, also all the eigenstates, if you take into account the SU2 symmetry. Okay, so that concludes the review of beta ansatz. Any questions? Okay. All right, then let me move on to the review of quantum computing. So as you probably all know, a qubit is a two-state system. And it's convenient and conventional to name the basis 0, which is 1, 0, and 1, which is 0, 1. And so for me, a quantum computer is a device that has n such qubits. We'll talk about what's this number in a minute. So the basis is given by a tensor product of this two-dimensional vector spaces. So x0 up to xn minus 1, where these x sub j's can be either 0 or 1, according to here. And you can regard these xj's as the binary bits of an integer x, right? So if I write x sub j times 2 to the j, and sum up from 0 to n minus 1, this is going to give me an integer x between 0 and 2 to the n. And so this is going to be, I can write my basis state this way. And there's going to be a 2 to the n such basis states when I have n qubits. And this is known as the computational basis. So a quantum computer can initialize each qubit to the state 0. So each of them will be, so I'll write a 0 and full tensor product. And we can perform unitary transformations on these n qubits. And these, turns out, one can decompose these unitary transformations into 1 qubit and 2 qubit unitary so-called gates or operators. As an example of a 1 qubit gate is the NOT gate, which we often denote by capital X, because it's in fact sigma x, the Pauli matrix sigma x, which is given here. And you notice that if I apply x to this guy, I get this guy. So x maps 0 to 1 and 1 to 0. So that's why it's called a NOT. And I can summarize these two statements in this simple one here, where little x here is 0 or 1, and this symbol here, this I'll call it O plus, denotes addition modulo 2. So x, big X on 0 is 0 O plus 1, which is 1. And big X on 1 is 1 O plus 1, which is 0. Another example is, an example of a 2-qubit unitary gate is the CNOT. So in here, this acts on 2 qubits, so say x and y. So here again, x and y can be either 0 or 1. And here, by the way, the tensor product is understood between x and y, and it acts this way. So the qubit here is often called the control qubit because you notice that it doesn't change. It was here x and it stays x, while this qubit here then is called the target qubit because it may change. It'll change to x and not of y if x is 1, right? If x is 1, we'll get here 1 O plus y. So y will go to the not of y. If x is 0, we'll have here 0 O plus y. So it's just y. It doesn't change. And that's why it's called a controlled knot, because it's a knot controlled by this control qubit. Okay, so this is a simple 2-qubit gate. And finally, on a quantum computer, we can perform measurements. So if we have some arbitrary n-qubit state, psi, so it's some linear combination of my computational basis, so alpha x are just some complex numbers, then I can make a measurement and that'll project that state into one of these computational basis vectors with probability given by the modulus of alpha x squared. So a device that can do this, that's a quantum computer. It's also useful to introduce a notion of a circuit diagram. So here we represent qubits by horizontal wires. So for example, my n qubit basis state, that's n qubits, so I can represent it by n horizontal wires. I'll label the top wire by the qubit here on the far right, so x naught, and then the bottom wire by the qubit here on the far left, xn minus 1. And then a shorthand for this is just to draw one horizontal line, but put /n, and that'll tell me that this is actually an n qubit state, xn. And also on a circuit diagram, we represent gates symbolically. So for example, if I have a NOT gate, I'll represent it here by a box with an X. And the C0, that being a 2-qubit gate, I'll represent using a pair of horizontal wires. So, so here, this bottom wire would be the control, and we represent it, denoted here by putting this circle. So this qubit won't change as a result of the C0, but then the top qubit here, the target qubit, may or may not change depending on the state of the control. And more commonly, people, instead of writing this, they'll represent the C0 gate this way, where this reminds you that this is an O+. And finally, on these circuit diagrams, the convention is that time flows to the right. So if I have a state psi, and then I act with U, and then I act with V, these are just two unitary operators, then the corresponding circuit diagram, I start here with psi. This is my n-qubit wire. Then I apply the U, and then I apply V. All right, so n, the number of qubits on current devices like IBM and Google, they're on the order of 100. Unfortunately, these devices are quite noisy. They make many errors. The dream, the fantasy, is that we'll have someday devices that have around, say, 10 to the 4 qubits that are fault tolerant, that they may have some errors, but then these errors can be corrected using something called quantum error correction. So we don't know when that's going to happen. Hopefully in my lifetime, maybe not. But in the meantime, we can test algorithms, so-called quantum circuits, using noiseless simulators. And in the work that I'll describe, that's what we did. We used these simulators, in particular those put out by IBM. It's called Qiskit. Those are available for free, and I encourage you to download and play with them. They're a lot of fun. And on those simulators, you can go up to 30 qubits. Okay, so that was the review of quantum computing. And now I'd like to explain how we could prepare so-called Dicke states on a quantum computer. So Dicke states are rather simple states. They're completely symmetric states of ones and zeros, these basis vectors that I defined. And we denote the Dicke states, D for Dicke and K. Okay, here's a reminder again, the zeros and ones are defined this way. So the K refers to the number of ones in the state. The N reminds us the total number of qubits in the state. So here we have N. So that means that the number of zeros is going to be N minus K. So as an example, if I look at the Dicke state 4-2, so these are 4-qubit states. Again, and then I have, and it's completely symmetric. with two ones. So here I have two ones here. I have the ones here, 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 and here. These are all possible ways of putting two ones. And so this is my Dicke state. And again, just a reminder about notation, this is a shorthand for 0, tensor 0, tensor 1, tensor 1. Okay. So one way you could think about constructing the state is start with a state where all n qubits are in the state 0, and then just apply the spin lowering operator S minus k times. That'll give you this Dicke state up to a proportionality factor. So here, this S minus is Sx minus Isy, where S is the total spin operator for n spins, spin halves, so like that. So this is quite familiar to everyone. And also, I should say that these states are exact ground states of ferromagnetic Heisenberg chain, and also this is the Hamiltonian. Excuse me, and also the so-called Lipkin-Meshkov-Glick Hamiltonians given here, which is just S squared. So these are interesting, but relatively simple states. And you could ask, really as a warm-up exercise for us, how to prepare such states on a quantum computer. Now, we cannot simply implement this construction on a quantum computer because quantum computers, as I mentioned, can only implement unitary transformations, and S minus is not unitary. So we have to do something a little bit more clever. And so instead, what we'll do is we'll start with a reference state, which is a simple product state, denoted by E and K, where K is the same K as here. So it's the number of ones. So it'll be just K-fold product of ones. And then we'll have N minus K fold product of zeros. So this is very easy to build on a quantum computer. You just need K not operators acting on the all zero state. And what we're interested in is a unitary operator. I'll call it UN, which when acting on this reference state will give us a Dicke state that we'd like. And so I'm going to call this the Dicke operator. And I'd like it to be, as I already mentioned, should be unitary, so I can implement it on a quantum computer. And also, it should be independent of K. Turns out this will make it easy to find what the operator is. And the key idea for finding this operator is to use recursion. And I'm following here this very nice recent paper by Bethe and Heisenberg. So coming back to my example of a Dicke state D42, notice that for these three states, they all end in 0. So I can factor it out. And what's left is also a Dicke state with one fewer qubit. Right? These are 3 qubit states. They each have 2 1s and 1 0. And then these guys here, they all end in 1. So I can factor out this 1. And what's left is, again, a Dicke state with 3 qubits, but only 1 1 because we factored out one of them. And if you mind the coefficients, you see that this Dicke state D42 is given by Dicke state D32, so a 3 qubit Dicke with 2 1s, and a D31, 3 qubit Dicke with 1 1, and these are their coefficients. And we can do this for any number of qubits, any Dicke state, and this is the formula. So Dn here, and these are both Dn minus 1. This has the same number, K, and this one has 1 fewer because I pulled out a 1. And so what I'm going to do is I'm going to use this formula here on both sides. So I'm going to eliminate the Dicke states here, here, and here in favor of this Dicke operator. Okay, and now I use the fact that this Dicke operator doesn't depend on the value of K because it's different. Here it's k, here it's k minus 1. But since it's independent of k, I can pull it all the way out. And this is what I have. And you notice what's left here is rather simple, state. And let me define a new operator, W, which when acting on my reference state gives me this sum of two states. I'm going to demand that this W also be unitary so that I can implement it on my quantum device. And also, to make it easier to construct, also independent of the K. So I'm going to rewrite this formula again on the next slide. So here, well, here's the formula for W. And then, and then this, and this formula here, writing this as W, we see that that now I have a recursion for the Dicke operator, un in terms of un minus 1, and this W. And now I can telescope this relation, and I get a formula for the Dicke operator entirely in terms of these W's. So here, this is an ordered product of these guys. So if I want to construct a Dicke operator, it suffices to construct these operators W. Okay. So how to construct the W's? Well, our strategy is going to be to look for some new operators, I's, which depend on M, and also an additional index L, in such a way when I act on the reference state, where the index, I'll call it now L prime, is less than L, it doesn't do anything. It just acts as identity. But when L prime is equal to L, it acts as W. So in other words, and here's a reminder that this is my reference state, just a simple product state. So in other words, these operators I, they perform the job of these W operators for a fixed value of L. And also, I'm going to demand that these operators, when this index L prime is bigger than L, that they'll leave this alone. It'll act as identity on this product. So in other words, these I operators are going to be ordered in such a way as to not interfere with each other. Then it's very simple to check that if I make this ordered product of the I operators, that they'll do the job of W. So I can write W this way. So then it suffices then now to construct these I operators. If I have the I's, I have W's, and if I have W's, I have my Dicke operator. Okay, so then how to construct these I operators? Well, let's summarize. This I, when the index is L, performs the job of W. That's how we define the I. And these reference states are defined this way. And W was defined to act on the reference state in this way. So if you stare at this a little bit, you'll see that, let's start here, that this state here is simply this state here. And this state here is exactly the same. And the state here is almost the same, except that the qubits in blue are swapped. What is 0 here is now 1, and what is 1 here is 0. So what it means is that these I operators effectively only act on 3 qubits. I called it the 0th qubit because I count from right to left. So 0, L minus 1, and L. So just on these 3 qubits, and it basically leaves these alone. And then here it swaps the blue ones. So 0 goes to 1 and 1 goes to 0. And L minus 1 qubit stays always at 1. And if I define an angle theta such that this is cosine theta over 2 and this is minus sine theta over 2, then I can implement this operator using the following operator. So this is now using the circuit diagram that I introduced earlier. So this is just a C0 gate here. This is a control target, another one. And this is a double controlled rotation gate. So these are two controls, and this rotation is just a simple rotation depending on this angle theta. So if these two qubits are in the state 1, it'll do the rotation. Otherwise, it leaves this qubit unchanged. So this is not obvious, but it's a 5-minute calculation, which I'll spare you. And that's it. Because I've given you I, which gives you W, which gives you the Dicke state. You can compute the circuit size, the number of gates, and it turns out it's of order m times L minus m. So it scales linearly with the size of the circuit. That's not too bad. So as an example, in the case of the Dicke state D42 that I showed you earlier, this is the entire circuit diagram. So this is the reference state. So we have two knots, and then these will be in the state 1, and these will be 0. That's my reference state. Then this is the gate W4, W3, and W2. And also one can generalize this construction. So we've generalized it to higher spins. So instead of n spin halves, we can have n spin s spins. And this we did in a recent work. Also, instead of staying with SU2, one can generalize to higher rank, so SUD. So these are the so-called qubits. So, and this we did in another recent paper. And even a quantum deformation Q analog of these states, we also worked out. But these are all different kinds of Dicke states. Okay, if there's no questions, then I'll move on now to the main point, which are these beta states. So to be concrete, I'm going to focus here on the closed periodic spin-and-a-half XXZ chain. So I explained earlier XXX. So this is just a slight deformation of that Hamiltonian. So now we're going to put a coefficient here, delta. In the case delta is 1, we go back to the Hamiltonian I showed you at the beginning. So this is called the XXZ spin chain. And we're going to assume that these beta roots, these quasi-momenta, K1 to Km, are known. And the question we want to ask is, how can we prepare the corresponding beta states? Well, I'll denote now as BLM. So B for beta, L is the fact that I have a L spin-and-a-halves, and M, I have M magnons or M overturned spins. How can I prepare those states, which I showed you earlier, on a quantum computer? So actually, there's been a fair amount of activity on this question. So in the first work by a group from Virginia Tech back in 2021, they developed an algorithm. So that algorithm was based on the coordinate beta ansatz that I described in the beginning. So their algorithm is probabilistic, and it involves using ancillas. So the idea would be that ancilla means additional qubits beyond those that you need, beyond those in the beta state. And the idea there is that at the end of the algorithm, you measure the ancillas. If the ancillas are all in the state 0, then you know that the so-called other qubits, the so-called system qubits will be in the beta state. But if the ancillas are not all in the state 0, then your circuit has failed and you have to run it again. So so there's a certain probability associated with generating the beta state. And then actually in some later work with some students, I showed that the success probability, the probability that you actually will get a beta state coming out of that circuit, actually decreases exponentially with M. And also this circuit is restricted to beta roots that are real. Then in a following year, a group in Madrid developed a different algorithm based instead on algebraic beta ansatz, which unfortunately I didn't have time to review. Their circuit is deterministic, unlike this one, which is probabilistic, but it used so-called QR decompositions to be done classically and of matrices that scale exponentially with M. And also, it still wasn't very explicit in terms of elementary gates that would be needed to prepare these states. Then also in Madrid, a year later, they developed a sort of algebraic coordinate beta ansatz approach where they proposed analytic formula for the unitaries. So what I'd like to describe today is work with David, which is based on coordinate beta ansatz. Here, the circuit is deterministic. It doesn't involve ancillas or these QR decompositions, and it's very explicit. It's basically a generalization of the Dicke circuit that I showed you earlier. So let's denote the beta state now this way. So here we have the set of all permutations of M1s and L minus M zeros. So for example, in the case of the beta state with 2 overturned spins, it would be given by, so this is given by this. There's going to be some normalization factor, which I'll omit for clarity. And then these coefficients are, as I explained earlier, at the beginning of the talk, given by this coordinate beta ansatz expression. The xj's here are the position, or are integers 1 to L, giving the positions of the ones in the W. So for example, here, the x's would be, this is 1, 2, so it'll be 3 and 4, where the ones are. The point is that these quantities F are known, and there's L choose M of them. So a key construction is something we denote by psi of B. So here, we're going to restrict to sum of all W's in the set PLM that I described in the previous slide of the form AB, where this means concatenation. So in other words, the W ends in B specified here. Once again, it means that I write W sum over all W's in this set of the form AB. That is, it ends in B. So, and this here is F of B is just a normalization factor. For example, going back to this B42 that I showed on the previous slide, you notice that these 3 vectors here, they all end in 0. So if I want psi of 0, that means I just choose these 3 vectors and I normalize them with 1 over F of 0. That's the meaning of this notation. And notice that if I take B to be the empty set, so then psi of the empty set is just all of B, so BLM. And the idea behind our algorithm is to do recursion, as in the Dicke state, over the length of this guy, we're calling over B. So we're going to define an unitary operator UM, which takes this sort of reference state to this state psi B for all B and for all values of little l. Yeah, so we're going to call this the beta operator. It should be unitary. It should be independent of L and B. And as I said, when B is the empty set, then this guy here is the beta state. And then this here reduces to this, what I showed here. And so this is what we're looking for. We're looking, in particular, this operator UL which will take this simple product state into the beta state. And we're going to do recursion, and the recursion is ridiculously simple. It's given here. Let me explain it with an example. Oh, I'm sorry. So this G here is a new quantity defined as a ratio of F's. So remember from the previous slide that, again, for B42, psi of 0 was given here. Now, notice that these two states end in 0, 0, whoops, while these two here end in 1, 0. So, so I can introduce, I can replace 1 over FB here in terms of G. That's what I did here. I wrote 1 over F0 as G00 over F00 on this one. And for this one, I wrote F of 1, 0 as G of 1, 0 over F1, 0. And then realizing that formula, that definition from the previous slide, this is nothing but psi 0, 0, because this guy ends in 0, 0, and it's normalized with F0, 0. And these guys end in in 1, 0, and they're properly normalized with F1, 0. And so we get this formula. In other words, if the state ends in B, it must end in either 0B or 1B. And so now what we're going to do is we're going to replace the psi b's on the right, on the left and the right side using this formula on the left to obtain a recursion for the beta operators. And we end up with a recursion like this, very similar to the Dicke one. We can telescope it to write UL as an order product over the W's. So it suffices to construct the W's. And we'll have a similar strategy. We'll look for operators I's, ML, such that they perform the job of W for a fixed L and all values of B. And they'll be ordered so as to not interfere with each other. And then these W's will be given by an order product of these I operators. And so it'll suffice to construct these I operators. And again, I won't prove it, but it's not difficult to show that, that this circuit here will do the job. It's reminiscent of the one I showed you for the Dicke circuit. This guy with a calligraphic U is given by a product over some unitaries lowercase u. So here we're multiplying over all possible b's for given values of little m and little l. And these u's here are these 1 qubit rotation gates involving angles theta, lambda, and phi, which are given in terms of these big G's that I introduced earlier. And this represents controls on these rotation gates, and these controls should be placed on those qubits where the B's have 1s. And that's it. So I apologize if it's a little bit fast, but let me just show you what that looks like. So if I go to the case, the beta state for a chain of 4 sides and M overturned spins, this is the full circuit diagram. So this preparing the reference state, this prepares the W4, W3, W2. Here, this corresponds to B being the empty set. B is 1, B is 0, 1, 0, and 0, 1. And if you, and these are the controls I alluded to here, for example, which differentiate between B being 1, 0 and 0, 1. And if you compare this circuit to the one I showed you earlier for the Dicke state, D42, it's almost the same. except for the rotation angles in these gates, this gate and then this control. So at least for the small Dicke states are almost the same. Of course, as you go to more and more sites, things become more and more different. It turns out that the circuit size is of the order L choose M, which is roughly equal to the number of free parameters, the number of coefficients, little f of w that I showed you earlier. So we expect that this circuit is roughly optimal. Nevertheless, for the maximum case where m is equal to half of the length of the chain, then L choose L over 2 is exponential in L, so it's not very satisfactory. So the circuit size is very large. So that's a problem with this with preparing beta states, exact beta states on a quantum computer. Okay, I guess I have still a few minutes left, so let me quickly show you a simple application of this circuit that I just explained. We can use it to solve beta equations in a way. So it turns out that beta equations are generally very hard to solve. And you could ask yourself, can quantum computers help? So there's a very popular algorithm these days for quantum computers known as variational quantum eigensolver, or VQE. So this is a hybrid quantum classical algorithm for estimating the ground state energy, E naught, of a Hamiltonian H using the familiar variational theorem. So let me show you how that works. So we start with some normalized trial state, which I'll denote as psi of theta. And these thetas are to be understood as a set of variational parameters. And we're going to do an iteration. So we can begin with, say, random values for these parameters. And then we'll compute the expectation value of the given Hamiltonian H using this normalized trial state. And the idea is to do this on a quantum computer. And then to update the values of the parameters. So from the nth iteration to the n plus first iteration, and this is done using a classical computer. So this could be done, say, using gradient descent or something like that to improve the parameters. And then you go back, and now you compute this expectation value using these updated parameters, and you keep looping until this expectation value converges, and then and that'll be your estimate for the ground state energy, because you know from the variational theorem that no matter which trial state you take, the expectation value is always going to be bigger than or equal to the true eigenvalue. So this is something people have been doing a lot in the last few years, especially chemists are interested in using this to determine the ground state energy, say, of some complicated molecule. So our idea is to estimate beta roots using this VQE algorithm, taking the exact beta states as the trial states, and then treating the beta roots as the variational parameters. And so this is something that we did in an even more recent paper. So so this would be a way of estimating the beta roots without actually solving the beta equation, but instead making use of this VQE algorithm. But to test this idea, we used classical simulators. So in other words, in this step, instead of using a quantum device, we just used our classical simulators. And of course, we did this updating also on a classical computer. I should explain that there's at least two kinds of simulators, classical simulators, and in this work we use two. One is a so-called Qiskit state vector simulator, and the other one's called the Qiskit air simulator. So this one performs matrix arithmetic exactly to compute exact expectation values. So that's not something a real quantum computer would do. Instead, this air simulator performs noiseless simulation using, and we chose 10,000 shots or trials. So this is closer to what a real quantum computer would do. It would just run the circuit, say 10,000 times, and get some kind of, and then compute things. You get a probability distribution, and you would use that to get your answer. Okay, so then we first tried this for the ground state beta roots. And so say choosing value delta equal 2 in the XXZ chain. Sticking to even values of size, so the length of 2, 4, and 6, then it turns out that the ground state lies in the sector where m is half of L, so here 1, 2, and 3. And we computed the energy in the true roots just with Mathematica. This is small system size. You can easily do this with Mathematica. And you'll notice that here the beta roots, here the k's are all real. And then we used this VQE approach and using the state vector simulator, and we got, the results were almost the same. Very, very accurate results. So it shows that this approach, at least in principle, can work. And then using the air simulator, which is closer to what a real computer would do, well, the results weren't as good, but still the agreement with the true roots is fairly good. And then we also looked at excited state beta roots. So those are harder to compute even classically. And using VQE, it's not so clear how to do it because the VQE is mainly for ground states. But what we did that instead of minimizing the expectation value of the Hamiltonian, we now minimize the variance. So the variance, is defined this way. So expectation value of h squared minus the expectation value of h squared, which is always bigger than or equal to 0, and it's 0 for exact eigenstates. So the idea to do this for VQE, I think, was first published here not too long ago. And again, for the closed chain with delta equal 2, so these are just some selected excited states, again, obtained with Mathematica. And here you see we have now some beta roots which are complex, as well as some that are real. Using this VQE algorithm, running with the state vector simulator, again, the agreement with the true roots is excellent. With the air roots, which again is closer to what a real device would give you, is not as good, but still fairly good agreement. Of course, on our simulator, we assume that there's no noise. Real devices have a lot of noise, so you couldn't do this on a current device now. Okay, I think I'm just about out of time, so let me quickly conclude with an outlook. I've shown you a deterministic algorithm for preparing exact beta states. Actually, it works for any U1 and any U1 eigenstate, not just beta states. So if you tell me the coefficients are called f of w, then this algorithm can prepare that state on a quantum computer. And then we use this algorithm for estimating beta roots. But sadly, we didn't exploit integrability really in this algorithm. As I said, it works for any state. So one can wonder whether one can do better, whether one can come up with an algorithm that will exploit integrability and maybe do this job more efficiently. Also, can we reduce the circuit size and or the depth, right? Because the size and depth, which is how many steps the computer would have to do to prepare to run the algorithm, is also growing exponentially in size, and that's a problem. Well, there's been recent efforts to exploit so-called ancillary measurements and feed-forward operations to reduce circuit depth. In particular, this group recently showed how Dicke states could be prepared with circuits that are, instead of being linear in depth, are actually constant in depth. So maybe these sorts of ideas could be used also for Bethe states. And also this group here was able to slightly improve on the size of the circuit. And also here I was restricting to spin-half qubits. One could think about extending to higher spin or even higher rank. Also, I restricted to models with U1 symmetry. You could think about even extending to models without this U1 symmetry. And there's many more questions, but I'll stop here and thank you for your attention.
Thanks very much, Rafael. It's a fascinating talk, and it's a very elegant solution to these problems,
Thank you.
to this type of simulation. There's one question in the Q&A panel from Harish Valluri, who asks, since you have an arbitrary choice of K in your initial reference state, is it possible to define a shorter depth Dicke circuit if you let your operators depend on K?
So I think I just, I think I understand the question, but let me go back to one. So maybe I can say it's in the context of Dicke. I think that question was asked in terms of Bethe states, but I think so the question was that whether here that had this assumption of being independent of K, and whether if I assumed it depended on K, if I could make it better. That was the question.
Yeah, I think the question was, can you define a shorter depth Dicke circuit if you let your operators depend on K?
Yeah, so actually in the work by Birchie and Eidenbenz, their U does depend on K.
Yeah.
But at the end of the day, I cheated a little bit here. I skipped some details, but it turns out it's the same. So with the way they did it, their U's did depend on K, and they got the same depth as what we got, and that's because I actually cheated a little bit. So when I told you this formula here, it turns out it's correct, but one can actually make it more efficient, have fewer, make it smaller, so reduce the number of gates by restricting this product here. You don't need all of these I's, you just need actually a subset of these I's, and that'll make it work. And that effectively makes U depend on K. So at the end of the day, my U really does depend on K, and right. I think that's the best we can do. Okay. So I did this just for ease of presentation, but in reality, one can go one step further, restrict the I's, so restrict the lower and upper limits. So depending on the value of K, so in effect, the U now does depend on K, and that does reduce the circuit size to the size I quoted, namely this. So the bottom line is that, the questioner is correct. By introducing dependence on K, you do reduce circuit size, but we don't know how to go below this unless you start playing these tricks of intermediate measurements and feed forward and these kind of fancy things. Yeah, thank you for the
And
question.
and then Eve Cheng had a question. Thank you for your talk. She says, is there a proof of completeness for the Bethe ansatz solutions?
Yeah, excellent question. So I believe that for the model that I gave, this XX Z spin a half, I believe now there is proof. So there's a rather mathematical proof by mathematicians. I think it's by Varchenko and company. And then there's a following work by Dima Volin. I don't have those references off the top of my head, but if that person can send me an email, I'll be happy to provide references. For many models, though, the completeness is still up in the air. But I think for this one, I think now there are proofs.
Okay. Zilin Lu starts off by saying, thank you for a nice talk. Maybe this is a silly question. There were no silly questions, only silly answers, right?
Exactly. Very good.
But he is interested in how to explain the degeneracy in the Bethe roots for the XXX model. Say the 0000 state is five-fold degenerate, as you mentioned earlier, but we have more than 5 ways to permute these qubits.
Yeah. So, yeah, and unfortunately, before the talk, I tried to connect my iPad to the EduRoam network, and I didn't manage. So I'll just have to use words instead of formulas. But okay, where is this quantum? I don't know what happened to the. Okay, here it is. Yeah, so the questions about this degeneracy, right? So the point is that so because you have SU2 symmetry, that means a Hamiltonian commutes with the 3 generators, right? Sx, Sy, and Sz, where these are the total spin operators. I think I defined them. When I was talking about Dicke states. Yeah, so these are the total spin operators. So there's 3 of them, Sx, Sy, Sz, and they commute with the Hamiltonian. So because that's what means SU2 symmetry. So in particular, S minus and S plus also commute with the Hamiltonian. So the idea is that if you start with the reference state, say, or actually any state, any beta state, it turns out that it's a highest weight state. That means that if I act on it with S plus, you'll get 0. Okay, so but then if I act with S minus on it, because S minus commutes with the Hamiltonian, the resulting state also commutes with the Hamiltonian, but that state will have Sz 1 less. And so what I do is I take the beta state and I keep acting on it with S minus, and that'll produce a set of states. And the number of those states, if you trust me, is exactly this number. So yeah, this L minus 2m plus 1. So that's how this degeneracy comes about. So the beta states are SU2 highest weight states, and then you act on them with S minus to lower them. And then those states, the number of those states is this number. And that's why you see that, so think of this as some beta state, highest weight state, and then it turns out it has spin 1. And so when I lower it, I get 3 more states. And that's where this comes from. This guy, turns out it has spin 2. So there's 5 of those states. So I lower it and I get these 5 states, and so on. is that clear to
I
the
think,
questioner?
yeah, I think
Okay.
that answers the question.
Yeah.
And the last question, Peter Drummond would like to know if your method can work, say, on current Google quantum computer with its universal gate set, or are these phase operators available on other standard implementations of quantum computers?
I caught almost all of it. Just the beginning. Could you repeat the beginning of it?
Oh, I'm sorry. Yeah, maybe I rushed. So Peter Drummond would like to know, are these types of phase operators available on standard quantum computers?
Phase operators. So
Yeah.
yes, so the gates that I showed are totally standard. So they're available on Qiskit, on the IBM machines, on the Google. Well, Google, I've never played with a Google machine. I'm not sure they're publicly available, but they have a simulator called Circ, and they're certainly available on Circ. So yeah, these are all standard gates.
Right.
Well, actually, let me double. I can one qualification. Let me show one of these circuit diagrams. Oh, that's too far. Yeah. So these 1-qubit gates. So the 1-qubit gates like NOT and the 2-qubit gates like the CNOT. These are, I believe, more or less native gates. So these guys here, these are double controlled rotations. So there is in the software like Circ and Qiskit, you do have these rotations available, but these are not native to the hardware. So what the hardware will do is that so when I'm not an expert on devices, but my understanding is that when you submit, say, a circuit to a real device, it'll take your circuit and will somehow compile it, just like in a regular computer, a classical computer would compile a program, and it's called transpile. It'll transpile your gates into native gates. So it would transpile these 2-qubit gates into more elementary 1 and 2-qubit gates. But so that's how I would try to run it on a real device. And even this one, it's not native, but you can write it in terms of 1 and 2-qubit gates. So that's what happens under the hood. So if you're just writing some high-level code, you'll never see that.
Right. Okay. So that answers the questions in the Q&A panel. Just thinking about generalizing to a broader class of problems that you might want to simulate on a quantum computer. I was thinking about things like, for example, trying to solve solutions to the Sine-Gordon equation, or problems on lattice dynamics, or affine Toda field theory, for example. A common approach is via the functional Bethe ansatz approach. But since these are all just different representations of the same problem, can this work be generalized to those sorts of problems which one might normally approach via the functional method?
So these are field theories. So that's so here I've been focusing on lattice models, which are kind of more amenable to, because these are just qubits after all.
Yes.
So
yeah, exactly. Yeah.
So I don't know how you would what would be the best way to simulate field theories. I mean, my guess is you'd have to discretize somehow.
Yeah,
so
it might be a lattice field theory, but of course, I imagine things would get so complicated so quickly it may be computationally prohibitive, even on a quantum computer. I don't know. It was just off the cuff.
Yeah, and there are lattice formulations of things like Sine-Gordon.
Yeah, there are.
But as you said, even they're all quite complicated. So yeah, I think my interpretation of the game is, try to find a problem which you can maybe solve on a quantum computer. And it's not so easy to find such problems, and then to actually find a way to to solve it. But
even problems where you might want to take into account more than just nearest neighbor interactions are going to become very complicated very quickly, right?
Well, I don't know. So yeah, and I should say, actually, that reminds me that here I was, so something like this is a control knot between a qubit here and a qubit, some distance away from it. And this circuit that I have will have such gates where the controls could be very far away from the targets. And this is actually also poses a problem to real hardware, because on real hardware, you have qubits in some kind of lattice or some kind of either one or two-dimensional lattice, and to be able to have controlled gates between qubits that are far away, this is not so easy to do. So and here I wasn't worried about these kinds of practical questions. So if you do worry about that, then it shows that it's even going to be more out of reach for sort of current technology. Absolutely. But if you're willing to just forget about those kind of complications, I don't see why long-range models should be any more difficult than short-range models. Okay. As long as you're allowed to put these kinds of gates between distant qubits, I think actually it would be interesting to try to simulate the Haldane-Shastri spin chain on the computer. I don't know if anyone has tried, but I think this could be pretty cool. And it should be doable. I don't know how efficient that would be, but it should be doable. Also, those wave functions are known, right? Haldane-Shastri told us, and those you don't even need beta ansatz. So I don't know. That could be a fun thing to try.
Yeah, very interesting. And as you said, the restriction for a real quantum computer might be in terms of the hardware implementation more than the algorithms. Yeah. Well, thank you very much, Rafael. That was a fascinating talk. I'll remind everyone that within a few days, it'll be up on the Australian Institute of Physics, Theoretical Physics channel on YouTube. So you'll be able to watch it there. And thank you for everyone for coming. And thanks very much for the time and effort in preparing an excellent presentation, Rafael. It was very
okay, David, it's been a real pleasure. Thank you very much.
Thank you. All right. Well, good afternoon, everyone, and we'll see you all again. Bye for now.
Bye-bye.